Okay, this is a demonstration how to do backward induction in a sequential game with perfect information but randomness. I will show it in this game digraph, which is based on the game Randomness with 5 stones and probabilities 2/3 and 1/3, meaning between every move of Anne and Beth there's a random move where 1 stone is removed with probability 1/3, indicated here, and with probability 2/3 the number of stones remain constant. So backward induction, these vertices here are the positions for n, where n is supposed to move, facing 5, 4, 3, 2, 1 and 0 stones. And the same here for Beth. Beth starts, well, the only position to consider with Beth is 4, 3, 2, 1 and 0. And these gray points in the middle are the random positions where a random move is supposed to happen. So we have 4, 3, 2, 1 or 0 stones left. And now, of course, in each case we have two situations: a random move where 0 or 1 stone is removed and the next player is Anne, or a random position where 0 and 1 stones are removed and the next player is Beth. As usual, we have to start at the end. It's backward induction, so we know the end positions. So no stones left. N supposed to move means N has lost, so the payoff for N is -1 and for Beth it's 1. And the same, of course, in the other case, no stone left. Beth supposed to move. Payoff is 1 for N, N has 1 and -1 for Beth. Now what we do is we want to get payoff labels for each one of these vertices on the digraph, and we move, of course, from right to left. We start with the 4 vertices on the right, like here. That is fairly simple, and I don't really want to discuss this a lot. Whenever we have only one move out of a position, out of a vertex, then we just copy the corresponding payoff. So in this case we have there's only one option for the random move, nothing left, nothing can be removed. So we take these two payoffs and copy them here. The same here for this situation, we go here. The 2 payoffs, we copy them here. And here is N, 1 stone left, there's no choice for N. N has to do this one, and this yellow color indicates that is what N will do in this position. Remember, she cannot do anything than that. So that means we take these 2 payoffs, 1 and -1, and copy them here. And the same for Beth here, only one option. So we have to go this way. We take the 2 payoffs and we copy them here. Next, what we want to do is we want to get the payoffs for this position. So we move a little further left. Now we have the typical situation of a random position, so a random move. And in random moves, backward induction means you have to take the expected value of the payoffs for this vertex. So we have 2 possibilities. Either no stone is removed with probability 2/3. You see the probability here on the gray arrow. And 1 stone removed is probability 1/3. Of course, the sum of these numbers must add up to 1. Now, what we do in this case is we calculate the expected value of the payoffs for N. Let me see. You see, we have 2/3, which is the probability for the first option to happen, times 1, which is the payoff for N. In this case, we have the product here. And we add 1/3, which is the probability for the second option, times -1. So again, the payoff for N in the second option. We do the calculation. 2/3 minus 1/3 is 1/3. So this 1/3 goes right here. We have to do the very same calculation for Beth. You see it here. 2/3 times -1. So 2/3 times -1 plus 1/3 times 1. 1 over 3 times 1 equals totally negative 1 over 3. So this negative 1 over 3 is a number which goes here. Expected value for Bass in this situation. We can do the corresponding calculation for this random position. We get payoffs of negative 1 over 3, 1 over 3. Again, first one is for n, second one is for Bass. The same kind of calculation, I don't really show it again. Next we look at this position. It's a human position, so in a human player position, the calculation is different. It's exactly the same procedure that you have done in sequential games without randomness. So what N does is she looks at the two options she has, removing one stone and arriving at a payoff of negative 1 over 3 for N, and removing two stones and arriving at a situation of a payoff of 1 for N. Now N, of course, focuses on the higher of these two values, which is a 1, and she goes for the 1, as you can see by the yellow color here, and the 1 is also copied there. Now it's important to understand that in this situation we don't do this calculation again for Bass because it's an N move. So what we do is we copy the whole black circle payoff for the position where N will aim to, and copy it here. So the black payoffs are just copied there. Next we do it for Bass here, the same procedure. Bass has two options, removing one stone, arriving at a payoff of negative 1 over 3, or removing two stones, arriving at a payoff of 1. So what will Bass do? Well, negative 1 over 3, 1. Which one is the higher one? Well, she obviously goes for the 1. So the arrow points to the higher of the two outcomes for the possible positions you can go to. And again, we will copy the whole pair of payoffs there. So you see it here, the black circled payoffs, both of them are copied down here to negative 1 and 1. Next one is a random position again. So what do? We do the calculation as usually. So we have 2 over 3 times 1 plus 1 over 3 times 1. We get a 1. So this is a little silly calculation. So for this reason I omitted it. If we have two outcomes and both carry a payoff of 1 for N, of course, the total outcome will also be a 1, and that's the same for the Bass position here. So this is some rather simple calculation. In principle, it's the same calculation I showed before, but it's not so interesting. For this reason, I kind of skip it and move to the next one. So here we go to N again. So what does N do? She focuses on the payoff here, negative 1, or the payoff there, negative 1 over 3. Which one is higher? Well, negative 1 over 3 is higher than negative 1. That means that is what she does. She goes to the negative 1 over 3, as you can see by the yellow color again. And she copies the whole pair, negative 1 over 3, 1 over 3 there. So keep in mind, we don't do this looking for the maximum twice. We do it only once, only for the corresponding player. For N, we look at the first entry. For Bass, we look at the second entry, and we copy the whole pair of payoffs to the corresponding position. Now the same for Bass, it's really symmetric. So Bass will certainly go here. I omitted the calculation because it's the same as it was before. Another random move, and a little more interesting than before. So what are the expected payoffs in this case? Well, we look at 2 over 3 and negative 1 over 3, and 1 over 3 and 1, and we do the calculation. 2 over 3 times negative 1 over 3 plus 1 over 3 times 1, so we get eventually a payoff of 1 over 9. We write it down here. And we have to do the very same calculation, but now for the blue, for Bass. So for random positions, you always have to do two calculations and always 2 times expected value. And again, of course, for 3 players, it would be 3 times, obviously. So for Bears, we look at 2 over 3 times 1 over 3 plus 1 over 3 times -1, and we get a payoff of -1 over 9. By the way, it's not a coincidence that these expected payoffs at every vertex here always add up to 0. It's a zero-sum game. So this will also happen between, that the expected payoffs at every position would add up to 0 in a zero-sum game. Okay, I skipped a few of these calculations. So again, another random move, another n moves here. So she removes 1 stone here in this situation. Bears moves here, she removes 1 stone. Again, why here? Because -1 over 9 is better than -1, so she certainly goes for the -1 over 9. And again, keep in mind this one is copied here because she goes there. Another random move, more complicated numbers for the calculation, but the calculations are exactly the same. Twice expected value calculations. And finally, an n move again. So which one is better? 5 over 27 or -1 over 9? Well, 5 over 27 is positive, so it's obviously the better choice. So we take the whole payoff pattern, 5 over 27, -5 over 27, and copy it here. And that means that the expectations for n in this game is 5 over 27. So n will more likely win the game than Bears. So the expectation is 5 over 27, which is about 1/5. So she will win more often than Bears. And of course, how do they play? Well, n will remove 1 stone initially. If n has 4 stones, she will remove 1 stone. If she has 3 stones, she will remove 2. With 2, she will of course remove 2 and win, and with 1, she will remove 2 and win as well. And you see for Bears, it's really symmetric. If Bears has 4 stones, removing 1, with Bears having 3 stones, removing 2, with 2 stones, removing 2, and with 1, removing the only remaining 1.